In our last two lessons, we've been looking at alkanes, which are saturated hydrocarbons. This means that I can't add anything more to them. I can do substitution reactions, but I can't do any addition reactions. I can't add chlorine to it or bromine or whatever. I have to substitute, remove something and then put something else in. What we're going to look at today are the first of the unsaturated hydrocarbons. This means we can add things to them because they don't just have single bonds. They have a carbon-carbon double bond in them, which is represented by a double line, or if you're typing, just use equals. Okay, so if you're doing it on a computer, just use the equals button to represent the double bond. They have a slightly different general formula because this double bond means there's two fewer hydrogens in them. So you'll find that, for example, here I've got 3-hexene. It's going to have 3 carbons there, 2 there, 1 there, 1 there, 2 there, 3 there. My quick maths says that's 12. So C6H12. If I look at a variety of alkenes, I see that same pattern. There are twice as many hydrogens as there are carbons. So if I add C12BH24, for example. Now that's assuming only one double bond. You can have polyunsaturated hydrocarbons, which means poly, lots of. That means more than one double bond in it. And you might have heard of the term polyunsaturated fats. They're the ones we say are good for you. So they come from things like avocado, and they're in oils and often in nuts. Those ones are the ones that are good for you. Omega oils are another good example from fish. They're polyunsaturated fats. They're fats with lots of double bonds. It means that your body can break them down a lot more easily. That's why they're better for you than the saturated fats like butter and lard and things like that. Okay. We also notice that the cyclics, because of that circle, that other carbon-carbon bond, you've got 2 fewer carbons again. So this one here, cyclohexene, would be C6H10. If it was cycloheptene, so 7 of them, it would be C7H12, and so on. So the pattern we see there is that it's times 2 minus 2. All right, so if you see that this is our general formula, it's probably going to be a cyclic alkene. Now you'll notice that I've underlined ENE in these. That's to help you with the naming of them. This is the suffix for anything with a double bond, and it doesn't matter how many double bonds it's got, you're always going to end in ENE. This year we'll only look at things that are monounsaturated, so one double bond only per molecule. So I'm not going to throw you what are called dienes or trienes and so on, where there's lots of double bonds. We're only going to throw you ones to name with one double bond. Okay. Remember our meth, eth, prop, but, must eat peanut butter, and our shapes to help remember our prefixes. So when naming them, we end in "ene", and we remember our rules for our prefixes as well. As well as that, there's different types of isomerism, and we've just had a little play with the molecular models to make as many C4H8s as we could. We had 2 cyclic alkanes, but what I want to focus on here are our 4 alkenes and how we name them. And I've used a bit of colour coding to help. I'll walk and talk you through this. Isomerism in alkenes can be broken down into structural and or geometric. Now, structural is just like our alkane isomers. The atoms are laid out in a different way. They're connected to different carbon atoms and so on. And that's what makes them a structural isomer. A geometric isomer means they have the same structure, but if I make a 3-dimensional model, they look a bit different. So their geometry is a bit different. And so for geometrics, you have to expand the structural formula a little bit more to show that isomerism. So let's go through the structurals first, because this is very, very similar to the ones that we've already met. The most obvious way to make a C4H8 is to have your 4 carbons in a row, and on the first one, make it a double bond. So I get CH2, CH, CH2, CH3. It's got a double bond, so it must end in ene. So I write backwards, remember. So I write ENE first. Then I go 1, 2, 3, 4 carbons in the longest chain. So it's a butene. Then I number them, 1, 2, 3, 4, and actually you would go 1, 2, 3, 4 backwards as well to check. And I see that the lowest number carbon that the double bond is on is number 1. So it's 1-butene or but-1-ene. You can write it either way. Okay. This one here doesn't have geometric isomerism because it's got 2 hydrogens on that 1 carbon. So it can't have geometric. I'll show you why that's important in a moment. Okay, and next one I've done is I've actually ripped off this CH3 and put it somewhere else. So I've put it on that middle carbon. And I've made this one here. So I've got my double bond at the start, then a carbon, taken that hydrogen off and put it on that CH2, and I've got my CH3 sticking off the side. My longest carbon chain is 1, 2, 3, or 1, 2, 3. I have to include the double bond in that carbon chain. I have no choice. Because it's an alkene, I have to include the double bond when finding my largest carbon chain. So the largest carbon chain with the double bond in it. Okay, so there's a bit of a proviso that makes it different to alkanes. So 1, 2, 3. And you'll usually have the double bond at the lowest number possible. Okay, so this is a 1-propene, but I don't need the number because if I put it there, that would still be carbon number 1. Okay, and if I put it there, it would still be carbon number 1. So I don't need the number. You wouldn't be wrong to put it in, by the way. So if you're unsure, put it in. So, ene, because it's got a double bond. 3 is my biggest carbon chain, so it's a propene. But it's got the side chain, so it's methyl propene. Again, if you wanted the number, it would be 2-methyl propene. But if I move it, it actually just makes butene again. So there's only one place it can go. So you don't need the number. Put it if you want to. It's not wrong to put it at this level. And our last one is the same as this one, but I've moved the double bond into the middle. And so I've made 2-butene or but-2-ene. Because this could be carbon 2 or carbon 3. 2 is a lower number, so we choose that one. Now, the reason I haven't written that there is because this one can express geometric isomerism. Because the groups on each carbon are different. The groups on each carbon are different to each other. So therefore it can have geometric isomerism. Please remember that because that's a definition, as it were. A molecule can have geometric isomerism if it contains a double bond and the groups on each carbon involved in the double bond are different. Okay, so it's saying that the CH3 is different to the H. Not that the CH3 is different to the CH3 or the H there. It's on the same carbon, there are 2 different groups. On the same carbon, there are 2 different groups. This can have geometric isomerism. That's why this one can't and this one can't, because these 2 have hydrogen coming off them. That's the same group, so it can't have geometric isomerism. The easiest way to remember this is I usually use the carbon chain because it's the easiest thing to look at. And in this one, the carbon chain creates the letter C if I turn it 90 degrees. And so the prefix for this is cis to butene, letter C. In this one, it goes across, it transverses the double bond. Okay? To go from this carbon to this carbon, I have to go through or across the double bond. Now, when I was young, I knew quite a good mountaineer, so I know the idea of transversing something, going across it, and mountaineering. But the prefix trans does mean across. So this one is called trans-2-butene. They have very similar properties, but not identical. Okay? They have the same chemical reactions, but they actually have slightly different properties because of the way the electron cloud is shaped. So we'll get to that in more detail next week. All I wanted to go through today quickly with you today is the general formula, this term unsaturated, meaning that it's got a double or actually a triple bond, polyunsaturated, meaning lots of double bonds, and that there are now 2 types of isomerism that are best shown by looking at molecular models or showing expanded structural formulae rather than the simplified ones like these. Naming, of course, putting the ENE suffix at the end, looking at our longest carbon chain to say whether it's eth, pro, bute. Should have put brackets around M because you won't have a methyl one. And so on. So the rules we've looked at are pretty much the same. Just remembering the longest carbon chain must include the alkene functional group. Okay? And those are our key ideas. In geometric, have a look at the carbon chain. Does it make a letter C? Or do you have to go across, transverse, the double bond to link up the carbons? And that's it in a nutshell. An introduction to alkenes.